Hello everyone, in this video I will go through several practice questions on continuous facility location. I will explain not only the final answers but also the logic behind each method. We will begin with a rectilinear minisum problem solved by the median method. In the first question, a company wants to locate a new warehouse to serve 5 retail stores. The goal is to find a location that minimizes the total weighted rectilinear distance. So here the important ideas are the meaning of rectilinear distance, the role of weights, and how the median rule helps us find the optimal coordinates. Now let's start with the calculation of x-coordinates first. The goal is to minimize the total weighted rectilinear distance. Since this is a rectilinear problem, we use the median method. The first step is to sort the stores by their x-coordinates and compute cumulative weights. The total weight is 25, so half of it is 12.5. This half weight value is the key reference point in the median method. Now we compare the cumulative weights with 12.5. The first cumulative value that reaches or exceeds 12.5 appears at the store with x is equal to 5. So the optimal x-coordinate is 5. This is the weighted median idea. We are not taking an average here, we are selecting the coordinates where the cumulative weight first passes half of the total. Now let's do the same thing for the y-coordinates. After sorting the stores by y value and checking the cumulative weights, the first value that reaches or exceeds 12.5 appears at y equals 4. So the optimal warehouse location is 5, 4. At this point, we already know the best coordinates. The only thing left is to compute the total cost. On this slide, we calculate the total weighted rectilinear distance for the point 5, 4. For each store, we find its horizontal and vertical distance to the warehouse, add them, multiply by the store's weight. After summing all stores, the minimum total cost is 97. So the final answer for question 1 is that the optimal warehouse location is 5, 4 with total minimum cost 97. Now let's move to question 2. This time the problem is based on Euclidean distance, which means straight line distance. So unlike question 1, we are no longer using absolute values and weighted medians. Instead we use the gravity method, which finds a weighted center based on the supplier coordinates and their shipment weights. To find the x-coordinates of the gravity center, we use the weighted average formula. We multiply each x-coordinate by its weight, add everything, and divide it by the total weight. From the data, the weighted x-sum is 82 and the total weight is 14. So the x-coordinates becomes approximately 5.85. We do the same thing for the y-coordinates. The weighted y-sum is 58 and dividing by the total weight 14 gives approximately 4.14. So the gravity method gives the location 5.85, 4.14. This point represents the weighted center of the supplier network. Now we evaluate this location by calculating the total weighted Euclidean distance to all supplier plants. For each plant, we use a straight line distance formula and multiply the results by the corresponding weights. When these values are added together, the total weighted distance is about 48.3. So the final answer for question 2 is approximately 5.85, 4.14 with total weighted distance to 48. Next, in question 3, the goal is a little different. We still have a rectilinear minisum problem, but now we want to write it as an equivalence linear programming model. The challenge is that the objective function contains absolute values, so we need a way to express those terms in linear form. So you can see the original objective function in this slide. We want to minimize the total weighted rectilinear distance between the new facility and the existing departments. An important point here is the x part and the y part are separable, so they can be modeled independently, but the absolute values still need to be transformed before we can write a linear programming model. To handle the absolute values in the x direction, we introduce two non-negative variables for each department, positive and negative deviation variables. These let us rewrite each absolute value term in a linear way while keeping the meaning of the model same. So this is a key modeling trick that converts the x part into linear programming form. We apply exactly the same idea to the y direction. Again, we define deviation variables and rewrite the vertical distance terms in linear form. So after this step, both the x and y parts of the original rectilinear problem are represented as a linear programming model. Finally, the optimal solution is verified using the median method. For the x values, the weighted median gives x equals 4. For the y values, it gives y equals 5. So the optimal location is 4, 5. When this point is substituted into the objective function, the minimum total cost becomes 34. Now let's move to the last question, which involves using the Westfield method. This is again a Euclidean mini-sum problem, but unlike the gravity method, this method is iterative. In other words, we start with an initial point and improve it step by step. In this question, the initial point is taken from the gravity method. Using the gravity method, the initial point is found as 3.75 and 4.75. This is our starting solution, also called iteration number 0. It is not yet the final Euclidean mini-sum solution, but it is a good first estimate before applying the Westfield's updates. Now the Westfield's formula is applied. At this stage, we calculate the distance from the current point to each facility and then use those distances in the update expressions. The idea is that the next point depends on both the weights and distances, so the method gradually adjusts the location towards the This final slide summarizes the iteration results. As the iterations continue, the coordinate changes become smaller, which shows convergence. The method approaches approximately 3.82 and 5.9. So this is the final approximate location for question 4. Overall, these questions show 4 important ideas in continuous facility location: the median method for rectilinear mini-sum, the gravity method for Euclidean location, LP formulation for rectilinear problems, and the Westfield's method for the iterative Euclidean optimization. Thank you for watching.